Hi everyone, Professor Bob Young here, and in this instructional video we're going to talk about parametric equations. So let's go ahead and take a look at it here. Here's the notes for this section. All right, it says suppose that t is a number in a given interval I. A plane curve is the set of ordered pairs xy where x equals f of t and y equals g of t for some t on the interval I. Now this variable t is called a parameter, and the equations x equals f of t and y equals g of t are called parametric equations for the curve. Now the orientation or direction of the curve is given by increasing values of t, usually in physics. So this variable t that's introduced into the xy system will allow us to look at graphs a little bit differently. So when we graph parametric equations, and I've got a bunch of examples that kind of go with your homework and stuff, so we can look at these. We're going to select some values of t on a given interval, and then for each value of t, use the given parametric equations to compute our xy rectangular coordinates. We're going to plot those coordinates and label t with them. And then down the line here, we'll talk about getting the t out, eliminating the parameter. All right, so let's have at it. Example 1. Graph the plane curve defined by the parametric equations x equals t squared minus 1 and y equals 2t. In the interval, t is between -2 and 2. So what we have here is we have our ordered pair set up. I've got t, x, and y here, introducing the parameter into the rectangular system. And notice I went ahead and put -2 to 2 for t values. And then what I did is I went ahead and plugged in those t values to get x and y ordered pairs. So for example, when t is -2 here, -2 squared minus 1, x will be 3. When this is -2, y would equal 2 times -2 or -4. So I just went ahead and did that for all the remaining t values. So let's go ahead and graph our first plane curve. All right, so I'm going to go ahead and take the ordered pair 3, -4 down here in the fourth quadrant and plot it. 0, -2, -1, 0. 0, 2, and 3, 4 here. And if you want to, you can go ahead and label your t values here. So this is -2, -1, t is 0 all the way up to 2. And then you can go ahead and connect the points. So it looks like we're going to have a parabolic curve here forming. So you can see, and this is how they tend to write these in textbooks. They'll put these little arrows here indicating the direction or the orientation of the curve. And there is our first parametric graph. For example 2, I threw in a few different parametric equations here so y'all could get the feel of it. This one says graph the plane curve defined by the equations x equals the square root of t and y equals 1/2 t minus 1. And t in this interval we're going to call between 0 and 16. Now when I see the square root there, I'm going to go ahead and let t be 0. I'm going to try to pick some nice square root numbers in here. I could put a lot of values. I don't want to put all 16 numbers 1 through 16 or fractions or decimals or anything and get crazy. So we'll put in some values where we can see the curve pretty well. I'll pick 4 as another nice square root number, 9, and 16. So I'm just trying to see enough of this curve here. So again, when I plug 0 in for t here, x is the square root of 0 or 0. Y would be -1, which would be 1/2 times 0 minus 1. For 4, x would be the square root of 4 is 2. When I put 4 in here, half of 4 is 2 minus 1 is 1. 9 would get you 3 square root wise, and then 9 halves minus 1 would be 7 halves, or 3.5 for you fraction people out there. 16 square root of 16 is 4, and then half of 16 is 8 minus 1 is 7. So there are rectangular ordered pairs that go with those t values. All right, I'm going to go ahead and plot the values now. So 0, -1 is here. 2, 1 is here. 3, 7 halves or 3.5, and 4, 7. All right, so again, we can label our t values. T equals 0, t equals 4, t equals 9, and t equals 16. Now, of course, you could have put 1 in for t, anything between 0 and 16, 2. You would have had some decimal fractional answers, which is fine. You would have still traced this exact same curve we're going to be looking at here. All right, so this is going to go up to here, and we'll go ahead and put our orientation of the curve or direction of the curve. All right, now what I want to do next is go ahead and eliminate the parameter on these. All right, so I'm going to go ahead and solve this first equation for t by squaring both sides of it. Now, we didn't do that in the first example, but we could have, and we would get t equals x squared. So what we want to do is try to take the t out of these and write them in terms of x and y rectangularly. So now I can take this x squared from the first equation and plug it in here for t and get the rectangular equation y equals 1/2 x squared minus 1. And most of you will recognize this as a parabola that is shifted down 1 from your previous studies. That with that 1/2 there is horizontally stretched a bit. I like to say fraction fatter there as well. All right. Now, when you write this rectangular equation, they may want you to provide restrictions on x and y. So notice when t was within these 0 to 16 parameters, it looks like our values for x were between 0 and 4, so they may want you to put this in some of the homeworks you will encounter, and the range or y values would be between -1 and 7, so watch out for those. All right, so based on that last example, this handout the notes may make a little more sense now. So if you go down to the bottom, eliminating the parameter, get the t out, we took our given parametric equations, we solved for t in the first equation here, and we said that t was equal to x squared. I always prefer to solve for t in terms of x when possible, and then we plug that back into the other equation to get y equals 1/2 x squared minus 1, the rectangular equation. So now I think we've done enough of these where we can see through all the notes and continue. Now, I know a lot of you are thinking, Young, where's the trigonometry in all of this? So in example 3, we're going to introduce our friends sine and cosine back. It says, graph this plane curve defined by the parametric equation x equals sine t and y equals cosine t when t is between 0 and 2 pi. So what we want to go ahead and do here is let's plug in our values from 0 to 2 pi that hopefully by now we know and love, our unit circle values. I mean, some of you are going, oh no, it's that darn unit circle again. All right, I just keep hammering and hammering that all semester, but we'll keep going with it. Now let's see how well you know your circle. When t is 0, the sine of t is 0, and the cosine of t, y, would be 1. At pi over 2, the sine is 1, the cosine goes to 0. Pi, the sine is 0, the cosine of pi is -1. Now I know you're following along and just popping those in as quickly as I am. 3 pi over 2, the sine is -1 and the cosine goes to 0. And back to 2 pi, we'll be back to 0 and 1 again. All right, so let's go ahead and plot these and see what happens. All right, now in class, a lot of you know I like to use colors, and on my videos, I'm going to as well. So I'm going to go ahead and plot the first ordered pair 0, 1 here. Pi over 2, we can put 1, 0 here. My writing tablet was a little smooth there, sorry, slipped. 0, -1, -1, 0, back to 0, 1 there. So if we go ahead and connect the dots here, you can see this circle. I'll try not to make it too ugly. Don't pick on my circles and I won't pick on yours. All right, so we can go from time t equals 0, t equals pi over 2, just like we did in the other problems, all the way around. T equals pi, and then t equals 3 pi over 2. And you can see on this one, the direction, since how they arrange these equations here is going clockwise, which I know those of you that love the unit circle, you always know we start and go counterclockwise, but the way this one is defined, it goes clockwise. All right, now Young, how do you eliminate the parameter on this one? Good question. I thought y'all would never ask. So what we're going to do is go back to some fundamental identities here. Let's take the sine square t plus the cosine square t equals 1 here. And guess what we're going to put in for sine t here? We're going to substitute x in here, which would make this x square. And for cosine plus y square equals 1. And back to your algebraic days, you can note that this is the equation of a circle with a center 0, 0, radius of 1. So once again, we have eliminated the parameter by using one of our Pythagorean identities, probably one of the most important ones in trigonometry. Example 4. In the following exercise, we want to eliminate the parameter t and then use the rectangular equation to sketch the plane curve represented by the given parametric equations. And again, we're going to use those arrows to show corresponding increasing values of t. Now note in this one we have x equals the square root of t plus 4, y equals the square root of t minus 3. And again, this one says t is greater than or equal to 0. So let's go ahead and again start where we can start seeing this curve. Now we obviously know that t has to begin at 0 because we can't have a negative value there. And again, I want to pick some nice square root numbers like we did in other problems like this. I'll put in 1, 4, 9. Now we could keep going forever and ever, but we'll stop there and see what it looks like. So when t is 0, x is 4, y is -3. When t is 1, we're going to get x is 5, y is -2. When t is 4, we're going to get 6 and -1. And when t is 9, 7 and 0. So we'll go ahead and plot those points and show the direction of the curve here. All right, so I'm going to bring some different colors here on this one just to keep it all exciting for you. So we'll go 4, -3 here. This is my pretty magenta color that I'm picking now. 5, -2. 6, -1. And 7, 0. So this one looks like it's going to be the graph of a line here. Let me see if I can find my line tool and make this pretty. And I did so. And then if you want to, we can put the arrow out this direction. Okay. So again, if they are asking you for domain and range issues here on this line based on this set of parametric equations, see, plotting the points is extremely important because on this one we can say the domain or x values must be greater than or equal to 4, and then the y values would be greater than or equal to -3. And I know some of you are thinking interval notation, which of course we can and should do sometimes, which we will. Okay, we'll put them both ways just to cover our bases. All right, now we'll go ahead and eliminate the parameter on this one. I always like solving this for x better first. So what I'm going to do is I'm sorry, solve for t first, my bad. Subtract 4 from both sides. So I want to go ahead and solve this first equation for t. So I think y'all will see the square root of t equals x minus 4. And squaring both sides, t would equal x minus 4 quantity squared, which I am not going to FOIL or do anything else with, but I am going to take and stick back in the second equation for t. Now I know somebody go, I'll tell you where to stick it, Young, but no. Let's go ahead and say that's y equals the square root of x minus 4 quantity square minus 3. Now what happens when the square and the square root meet? My friends, you know, um, goodbye. And you're going to have x minus 4 minus 3, or you will eliminate the parameter and get y equals x minus 7. Now notice if we had the whole line graphed here, it would begin at 0, -7, and then rise 1, run 1 to get the rest of this line. But our parametric equations have limited the parts we can see. So I hope as we progress in this, you're starting to see things better and better when you get to that homework. In example 5, we're going to look at another trigonometric set of parametric equations. Again, this will result in a circle. Now you can also result in ellipses and hyperbolas and other creatures as we continue this, but I'm just staying with circles to keep those college algebra students in the loop here. So these parametric equations are x equals 3 cosine t, y equals 3 sine t, again from 0 to 2 pi. We'll graph this and eliminate the parameter here. So once again, I'll go ahead and assign some t values. So we'll go ahead and put in our quadrantal or quadrant angles, as your textbook likes to call them, 0, pi over 2 pi, 3 pi over 2, back to 2 pi here. And again, we'll see how well you know your unit circle. So the cosine of 0 is 1 times 3. X will get you 3. 3 times the sine of 0 radians. Of course, you could put your calculator in radian mode and get these answers as well. 0. Pi over 2, 0. Would get you 3 for y there. The 3 times the sine of pi over 2 is 3 times the sine of pi over 2 is 1, of course. Pi, -3, 0. 3 pi over 2, the cosine of 3 pi over 2 goes back to 0, sine -3, and then we're back to where we started here. So let's plot this creatures. So 3, 0, 0, 3. So this one's kind of heading the direction of our positive angles on this one, like the other one, the first example did not. -3, 0, 0, -3, and then back here. All right, so we can label this if you want to. T equals 0, t equals pi over 2, and then we can do this all the way around. And I might just take a shot at my circle tool here before y'all laugh at my circles until it gets back, and see if I can make a pretty one out of this. All right, I'm going to say the circle tool was a bust trying to do that. So anyway, it's as close as I could get here. It's not too bad. All right, so let's go ahead here and show you how to do this one. Now on these, we're going to have to divide both sides by 3 to get the cosine of t equals x over 3, and the sine of t equals y over 3. And then once again, we can go ahead and put it into our fundamental Pythagorean identity here. Cosine square plus sine square t is 1. And then substituting in these values, you will see, sorry, that should be a y there, that we will get x squared over 9 plus y squared over 9 equals 1, squaring these two creatures and multiplying through by 9, voila, there is our circle centered at 0, 0 with a radius of 3, and once again we have eliminated the parameter. In example 6, It says find two different sets of parametric equations for the given rectangular equation here, and you've got y equals 6x minus 4. So we can write infinitely many sets of parametric equations for a given rectangular equation by substituting in certain x values, let t be certain x values, and so forth. So let's look at this. All right, so for this first parametric equation, it says let x be t. So this one will be real easy to see here if you're looking up here at this equation. So you would get y would equal 6t minus 4. So your parametric equations for this would just be x equals t and y would equal 6t minus 4. Now, if x equals t minus 1, we could just take that and plug it in here to get another set of parametric equations for this. We would get 6 times t plus 1 minus 4. So if x is t plus 1, then y would equal distributing 6t plus 6 minus 4, which would give us 6t plus 2. So again, you can write infinitely many parametric equations based on a given equation here. All right, a similar example here. Let's take, it says find two different sets of parametric equations for this equation, rectangular, y equals x squared plus 9. Now again, when x is t, y is going to equal t squared plus 9, so that's kind of an easy one to see. But let's say if x is t cubed and they start messing with you, you would say that y would equal, now again, putting this in here, t cubed squared, so they may have some algebra involved in this, would give us t to the 6th power plus 9. So they will give you several of these different sets of parametric equations given a rectangular one here. For example 8, it says sketch the plane curve represented by this given set of parametric equations and then use interval notation to give each relation's domain and range. So to save time on this one, since we've done several examples now, I went ahead and put our quadrant angles from 0 to 2 pi. So again, I'll just show you one here. If you put 0 in for angle t here, the cosine of 0 is 1 times 2 is 2 plus 4 is 6. And then y would be negative 2 in this case. And then you can check all of these other angles as well. So if we go ahead and plot this one real quick, we'll get 6 negative 2. 4 negative 3, 2 negative 5, 4 negative 3, and 6 negative 2, 4, let's see here, 6, crap. All right, to conclude this lesson, I wanted to show you something kind of cool I would have shown you in class using our graphing calculator tool that's in our Canvas classroom, desmos.com, which we've been using throughout the semester. And we want to thank those people for offering up this great tool here. I wanted to show you how to graph some parametric equations and check them in Desmos. So I'm going to go back to example 1 here. And we said that the x value was in the parametric equation t squared minus 1. And I'm going to put comma, the y value was 2t. I'm sorry, and we graphed that. And if you remember, we said the interval was from negative 2 on t to 2. So look at the graph that we did. It's much nicer than mine. I know you'll appreciate that. Okay, so let me go ahead and hit enter here. Now, if you want to find a way to trace this along the curve, we'll show the direction of the curve. This is a pretty cool feature as well. I'm going to go ahead and put a different variable in here instead of t, just to show you the direction of the curve on this. And This works a little differently with Texas Instrument graphing calculators and Casios and other ones here. So I'm just going to substitute in another letter. It can be any letter for this. And what it's going to do is it's going to add a slider here. So I'm going to put a slider here. And again, I want to put the slider between -2 and 2. So this is kind of cool here, and you don't really have to hit the step here. And watch what happens. It's going to bounce back and forth here. Now, notice it would start down here when we did our first example. And if you want to, you see these little things over here. You can go ahead and just send that the direction it should go. All right, so what this does, it's an animation mode. It will track that direction from -2 to 2 forever and ever. So that's a really cool feature on Desmos. And we'll try one more here. All right, so for one of our other examples, we were writing different sets of parametric equations here. So I went ahead and let x be t. I think this was a couple examples ago, and y was 6t minus 4. And again, if you want to, we can go ahead and just put another letter in there. We'll put a in there for this. So you can have lots of fun playing with parametric equations at home. And we'll add a slider here. And we'll also go ahead and change this animation mode so we can see where it goes here. Oh, that one went pretty fast. I don't know if you saw it, but it was tracking along this. There it goes again. It's just doing it over and over again. Maybe I'll go ahead and put -10 to 10 in here. It always helps if you match up your numbers as well, and I think you'll see it a little bit better now. Let's try it. It's still going pretty fast along that curve. There, zipping by there. All right. Now let's take the other equation here and put it in here as well. Let me go ahead and get out of this and pause for a second. Now remember, we let t be, I think it was t plus 1 on this one as well. So let me just go ahead and back off of this, and we'll type in a second equation. All right, so looking at what I just did here, remember we put in t plus 1 for t, which made the y parametric equation 6t plus 2, and voila, the same line here. So when I go ahead and show this one here, it's going to have the same path, and I did find a way to slow that down a little bit when it was jetting through there. So it'll keep going that direction along that curve there. So you can have infinitely many equations representing the same parametric equation. Now, one other thing here, watch what happens if I were to, let me just go ahead and stop this real quick. We can negate t here, which shifts the line around, and let's negate the a value as well, and then run this animation again. It's still going in the same direction, but depending on what values you put here, it could totally change the direction 180 degrees and about. So very interesting things when it comes to these equations. So I think you should have enough now to complete your homework on this. Bob Young signing off, Parametric Equations. Bye.